All right, next topic is conservation of energy. It is corresponding with problem number 9, and it's a pretty big topic. So let's get right into it. There's basically two types of energy: potential energy, represented by a U, and kinetic energy, represented by a K. This is always just like the energy you have by moving, and U is the potential to like convert into kinetic energy, or the potential to do work. And it could be in many forms. It can be like gravitational potential energy. It could be like electric potential. It can be elastic potential, like in a spring. And the main idea is that energy is conserved, meaning that U1, U initial plus K initial equals U final plus K final. And this is assuming that you're not injecting energy or taking out energy of the system. And the full formula is a lot more complicated. It has a bunch of different other ways that energy is lost, such as like temperature or heat and stuff like that. But the main idea, and we're assuming in most of these questions, that energy is conserved, and that it's just U1 plus K1 equals U final plus K final. Now the way we find each of these energies, K is always measured in mv squared over 2. It's in joules. U can be measured in a bunch of different ways depending on what type of energy we have. Elastic potential energy, it's just 1/2 kx squared. Gravitational potential energy, it's mgh. Bunch of different types, and depending on what we use, we plug in different formulas for that. And then basically we just solve for the unknown, and we solve for converting a certain amount of potential energy into kinetic energy, or vice versa. And then another kind of main idea here is like when kinetic energy is at a maximum at any point in time, this is going to be at a minimum due to the fact that they have to add up to a certain constant energy that they started with inside the system. So when we're trying to solve for a situation when kinetic energy is at a maximum, we need to find scenarios where this is either 0 or as close to 0 as we can get it, and then that makes the problem a lot easier. So let's go into problem number 10, which I think is the most difficult problem on this practice test. It is very complicated, and the full proof takes a really long time, but I'll try to go over all of it anyways. So it asks about the minimum radius when we have these two particles. I can just draw them here. A is moving and B is at rest. And they give us a formula: potential energy equals U beta over R squared. Meaning that the closer they get together, the more potential energy is, the more like it really wants to shoot them out going fast. So this is kind of like a scenario where we have like two electrons or two protons getting really close to each other. They're repelling each other. That's kind of a similar idea in which you get closer together, they really want to repel each other. There's a lot of potential energy. So it asks us to find R minimum, which we know the minimum distance is going to create the maximum most potential energy. At that moment, when R is at a minimum, there is the highest number of potential energy in the system, due to the fact that when R gets small, U gets big. So therefore, we know at that time when potential energy is maximized, that kinetic energy will try to be minimized, and that's the whole point of trying to find when kinetic energy will be minimized. So the left-hand side of the equation is pretty easy. It's just the initial energy that we start with, and U1, I guess this is the main formula, U1 plus K1 equals U2 plus K2. And the left-hand side is pretty easy. We start with the potential energy of the initial. We're at a radius of 2d, so it's going to be beta over 4d squared. And the initial kinetic energy, this B particle isn't moving, and A particle has a speed of v naught. So the kinetic energy is 1/2 m v naught squared. And by this left-hand half of the equation, we can already eliminate answer choice A and E, as they do not have the correct number of initial energy as it should be. So then, at this point in time, we know that U is at a maximum. They even just give us the radius R min equals beta over R min squared. That's the U2. And so the hardest part is finding K2, which is really tricky. And a lot of people might think that we could just assume it's 0 because that's when U is going to be maximized. But if we think about A already has initial velocity V, and based on the laws of momentum, A, or mass, if they have the same mass times V naught equals mass times A, VA plus mass of VB. So there are two masses, or there are two velocities, have to add up to the initial velocity, meaning that there's never going to be a point where there's zero velocity, there's never going to be a point where there's zero kinetic energy. So this equation is still pretty important that the two final velocities have to add up to V naught, but we can't just assume that kinetic energy is 0. We have to come up with a way to minimize the kinetic energy. And the fact that we have another equation for this is pretty helpful because we can set up an equation, kinetic energy equals 1/2 m VA squared, and we're going to call VB equals V naught, which is a constant, minus VA. That's kind of just substitution we're doing there just to give us one variable. So KE equals 1/2 MVA squared plus 1/2 M V naught minus VA squared. So this is the equation of kinetic energy. We can simplify this a little bit to factor out a 1/2 M, so times VA squared plus we can do the binomial VA squared minus 2 V naught plus V naught squared. This can be simplified into 2A squared. And so now we have a formula for kinetic energy, and we need to find when it is at a minimum. So basically, taking the derivative of this with respect to VA, that's our only variable here, is going to be pretty easy. It's going to be, this is just a constant, so it can come out 1/2 M times product rule. This becomes 4 VA. Oh, this should be VA. V naught, I messed this up. But this becomes minus 2 V naught. And this part is a constant, so it goes away. And so when we're optimizing it, we set this to equal to 0. This we can cancel out. And the situation in which this is optimized, or I guess minimized in this situation, is when VA equals 1/2 V naught. And we can see if we plug this into the situation, we get 0. It's pretty clear. We don't really need to do a second derivative test, but this will make it to be a minimum, not a maximum. And it kind of makes sense that the minimum is when they each have half of the initial energy. But basically, we know what VA is. It's the same thing as VB because they're both 1/2. So K2 is equal to, they have the same energy, so we can do 2 times 1/2. That cancels out. M, the speed is V naught over 2 squared. That is answer choice B. Yeah, so pretty tough problem, but we got through it, and the answer is B.